double and half angle identities. The goal is to verify other identities using these two. Let's begin. The double angle identities. There's a double angle identity for sine. By double angle, I just mean, okay, if you take the sine of twice some angle, theta, then we can actually write that in terms of theta. It turns out that the sine of 2 theta is 2 sine theta cosine theta. It turns out this is easily shown to be true. All you'd have to do is, on the left side, replace 2 theta with theta plus theta. And then remember the sum identity for sine. So in this case, the sine of theta plus theta, alpha is theta and beta is theta. And if you recall the identity for the sum of two angles, turns out that the sine of alpha plus beta is the sine of alpha. I'm going to fill in the blank in a second. Actually, you know what? I'm going to run out of space here, recording space. So let me put the right hand side down here. Remember, the result is sine. Okay, I'm going to fill in the blank in a second. It goes sine cosine plus sine cosine. And then the way I write it anyway. And then it would be alpha beta here, alpha beta, and then beta alpha. But they're both theta in this case. So it would be theta theta, theta theta. And these are like terms. You have 1 sine theta cosine theta here, 1 sine theta cosine theta here. How many do you have all together? You have 2 of them. 2 sine theta cosine theta. It's that easy to prove, the double angle identity for sine. Okay, there's various versions for cosine. The cosine of 2 theta, the one I commit to memory is cosine squared theta minus sine squared theta. Now, where does that come from? Well, you could prove it much like we did this one for sine. Replace cosine 2 theta with cosine theta plus theta, and then use the sum identity for cosine. But what I really want to show you is where different versions of this identity also exist. So another version of this identity is 2 cosine squared theta minus 1. Another version of this identity is 1 minus 2 sine squared theta. And so I think the real question then is, where do these other versions of the right-hand side come from? Well, they come from this identity, cosine squared theta plus sine squared theta is equal to 1. Because if you solve, for instance, for sine squared theta, in other words, subtract cosine squared theta from both sides, you get sine squared theta is 1 minus cosine squared theta. And if I make that replacement right here, and remember to distribute this negative, there's where the minus 1 comes from. If I distribute the negative, I'll have a plus cosine squared theta. And if I add that here, I'll have 2 of them. And then you could do something similar with cosine squared theta. You could replace cosine squared theta. If you solve both sides of this equation for cosine squared theta, you get 1 minus sine squared theta. So if you replace cosine squared theta, on the other hand, with 1 minus sine squared theta, And combine like terms with this sine squared theta, you'll have minus 2 sine squared thetas with the minus 1 in front. So you get 3 right-hand sides here for cosine of 2 theta. And then for tangent of 2 theta, again, you could just use the sum identity for tangent to verify that the tangent of 2 theta is equal to 2 tangent theta divided by 1 minus tangent squared theta. And we actually proved this in the previous class as well, if you look back in your notes. Okay, let's get some practice working with these identities. Let's write in terms of a single trig function 2 cosine squared 2 beta minus 1. Now, this formula looks a lot like the right-hand side of one of the identities up here. In fact, it looks like this, except for the angle here, it looks like this. So let's write down the formula we're going to use here, the identity we're going to use. Oh, and by the way, there's a joke that goes with these double angle identities. It goes like this: why can't you trust the sine and cosine functions? Because they have double identities. Yeah, I know, it's a lame joke, but it's all I got. Okay, let's write this down. So here we go. The identity I want to make use of is one of the double angle identities for the cosine of 2 theta. Turns out that's equal to, one of the right-hand sides is 2 cosine squared theta minus 1. Okay, so is it a problem that this theta doesn't match up here? No, in fact, we treat it like a substitution. We just say theta is equal to 2 times beta. And then if we actually make the substitution, we can accomplish the goal of writing the given formula as a single trig function. So I'm just going to replace theta, the left-hand side in this identity, theta, with 2 beta, and rewrite the given formula as the cosine of 2. I'll put in parentheses here, although it's optional to put in these parentheses. The cosine of 2 times 2 beta. Like that. So I'm replacing the theta here with 2 beta. And so what do I really end up taking the cosine of? It's really the cosine of 4 beta. So I've accomplished the goal. I've written this given formula here in terms of a single trig function. And that's all we were asked to do in this one. Okay, next let's talk about the power reducing identities. In the power reducing identities, well, for instance, in this first one, we have the cosine squared theta, so we're squaring the cosine function. And the claim is that that's equal to 1 plus cosine 2 theta all over 2. So what's happening here? Oh, okay, we're reducing the power, but the cost of doing that, according to this identity, is that we end up taking the cosine of a double angle. That's cosine of 2 times theta, along with some other stuff. So where does this formula come from? Well, as you might have guessed, it comes from the double angle formula. So cosine 2 theta, it's the one involving the cosine squared. So 2 cosine squared theta minus 1. If you simply solve this for cosine squared theta, in other words, add 1 to both sides and divide by 2, you get exactly this first identity here. Okay, the second identity involves sine squared theta, and it looks a lot like the first one, except there's a minus right here. Sine squared theta is equal to 1 minus cosine 2 theta all over 2. And the tangent squared theta is equal to 1 minus cosine 2 theta all over 1 plus cosine 2 theta. And so you could prove these other two identities in similar ways to how we proved cosine squared theta equals this right-hand side. So I won't bother you with those details. From these identities, we obtain the half-angle identities. Now, substitute in to theta alpha over 2. Think about that. If you substitute alpha over 2 in for theta, then what does this become over here? Well, 2 times alpha over 2 becomes just cosine of alpha. And if you keep that in mind, then you'll know where the half-angle identities come from. The half-angle identities. If you let theta equals alpha over 2, and then you take the square root of both sides of that identity above, you get exactly the cosine of alpha over 2 equals plus or minus. It depends on which quadrant alpha over 2 is in as to whether or not it's plus. For instance, in the first and fourth quadrant, you'd get the positive root. In the other quadrants, you'd get the negative root. If alpha over 2 is in the other quadrants, you'd get the negative root. So cosine alpha over 2 is plus or minus square root of 1 plus cosine alpha over 2. Sine alpha over 2 is equal to plus or minus square root of 1 minus cosine alpha over 2. And then tangent alpha over 2 is equal to plus or minus the square root of 1 minus cosine alpha all over 1 plus cosine alpha. So for tangent, you can see where we got that first identity from. If you make the substitution, just take the square root, you get the tangent alpha over 2. It's not immediately clear where these other ones come from, but we'll talk about that a little bit later. So we've got two other identities for tangent alpha over 2. Sine alpha divided by the quantity 1 plus cosine alpha, that's equal to tangent of alpha over 2, and so is the quantity 1 minus cosine alpha all over sine alpha. Okay, let's work an example that makes use of the half-angle identity. In this example, we want to find the exact value of the cosine of 105 degrees. Problem is, 105 is not one of our special angles, so what do? We double it essentially. So take a look. I'm going to rewrite the cosine of 105 as the cosine of 210 over 2. So the idea, off to the side here, the idea is that you take 2 times the given angle and then divide by 2. Same thing, right? So why? Why did I do that? Well, 210 turns out to be a special angle. The reference angle for 210 is, if you think about it, you take 210, since it's in the third quadrant, you subtract 180 and get 30 degrees. So if I can figure out a way to write this just in terms of cosine of 210, I can go ahead and get an exact value that way. And of course, we have a way to do that. We have the half-angle identity for cosine, which says that the cosine of alpha over 2 is plus or minus the square root of 1 plus cosine alpha all over 2. So what's acting like alpha here? Well, 210 degrees is our alpha. Okay, so we fill it in. First of all, you have to decide which is it, plus or minus. Cosine 105 is in the second quadrant, so it's going to be the negative root. It's one or the other. And since we're ultimately taking the cosine of just 105 degrees, it's got to be the negative root. Okay, and then we fill this in 1 plus cosine of, okay, alpha is 210. And then all that over 2. This is all going on underneath the radical. So, okay, how do we simplify this? Let's separate the scratch work here. Keep it over there. Okay. How do we simplify this? First of all, let's take the cosine of 210 degrees. We know that 210 is in the third quadrant, cosine's negative there, so we're going to end up with negative cosine of the reference angle, which is 30. Cosine of 30 degrees is root 3 over 2, so cosine 210 is negative root 3 over 2. Okay, so in here we're going to replace, underneath the square root rather, we're going to replace this guy with negative root 3 over 2. So we end up with 1 minus root 3 over 2 all over 2, and all of this is underneath this radical. Now you might remember from algebra that we don't like having fractions within fractions, so one trick for getting rid of this denominator of 2 is to multiply the numerator and denominator of the big fraction. And by the way, this is all going on underneath the radical, right? Multiply the numerator and denominator of the big fraction underneath the radical by 2. The division bar is a grouping symbol, so we distribute this 2 into this numerator. So I'm going to distribute it like so. Put the 2 right there. It'll end up being in the numerator of this little fraction. And then distribute it here. So we get the opposite of the square root of 2 minus 2, that's the one I distributed, times root 3 over 2 all over 2. The whole point of doing that is these guys cancel, and therefore we get rid of this little annoying denominator within our bigger fraction. So we get the opposite of the square root of 2 minus root 3 all over 2. Oh, except I forgot one thing. You have to multiply this 2 by this 2 as well. So let's fix that. And we do get 4 there. Now, the radical splits up over division. Not over subtraction, but over division. So we can split this up even further as the square root of 2 minus root 3 all over the square root of 4. And of course the square root of 4 is 2. So we have finally the opposite of the square root of 2 minus root 3 all over 2 as our final answer. Okay, let's do a similar example for sine of 3 pi divided by 8. Okay, 3 pi over 8 is an angle in the first quadrant. I know that because 3/8 is less than a half, right? And pi over 2 is the same as 90 degrees. So it'd have to be 4 over 8 pi to be at 90 degrees. So 3 pi over 8 is in the first quadrant. So sine of 3 pi over 8 is positive. However, 3 pi over 8 is not a special angle. So I'm going to use a trick, just like I did in the last problem. I'm going to double this angle. So I'm going to take the sine of 2 times 3 pi over 8. Oops. And then I'm going to divide by 2 to compensate. Okay. The thing is, if I simplify now the numerator, it becomes 3 pi over 4. 2/8 reduces to 1/4. And so I end up with getting the sine of a half angle, 3 pi over 4 divided by 2. And so the idea is 3 pi over 4 is a special angle. And in fact, I can use my second formula up here for half angle. It looks much like the one for cosine, but now it's the sine of alpha over 2 equals plus or minus root 1 minus cosine alpha over 2. That's the one I'm going to use, where alpha is 3 pi over 4. And since 3 pi over 8, the angle I'm actually taking the sine of is in the first quadrant, we'll be taking the positive root. Okay. So let's fill it in. We get the positive square root of 1, this time it's minus cosine of, okay, alpha in this case is the 3 pi over 4. This guy is acting like alpha now. And then it's that whole thing underneath the radical divided by 2. Okay, 3 pi over 4, a little bit less than pi, is in the second quadrant. Cosine's negative in the second quadrant, so the cosine of 3 pi over 4 is negative. And its reference angle is pi fourths. So if you replace cosine of 3 pi over 4 with what it's equal to, okay, you get this minus is there from the get-go. And then minus cosine 3 pi over 4 is negative, rather, radical 2 over 2. Okay? And so you get that that's equal to the square root of 1 plus radical 2 over 2. The whole thing divided by 2. Minus minus makes the plus. We're going to use the same trick we did up above to get rid of the fraction within the fraction. Underneath the radical, I'm going to multiply the big fraction defined by the big division bar by 2 over 2. And you have to remember to distribute. So distribute here, and it'll end up in the numerator here, but not underneath the radical, right? So actually, it might be better to think of it distributing it right there. And so what does that do for you? Well, it gets you the square root of 2 plus, okay, 2 radical 2 all over 2. If you distribute this 2 right here, and then all over 4. And this is all going on underneath the radical. But of course, these guys cancel. That was the whole reason for distributing this 2 up here. And you get the square root of 2 plus radical 2 all over 4. And the radical splits up over division, so you could write it as the square root of 2 plus radical 2 all over the square root of 4 is 2. So there you go. Okay, in this example, suppose we're given the sine of an angle theta is equal to negative 9 over 41. And you're told that theta is in quadrant 3. You're asked to find the sine of 2 theta. Well, this is going to look a lot like problems we worked from chapter 5. Let's draw a helper triangle. Since we're given that theta is in quadrant 3, draw the helper triangle in quadrant 3. So the assumption is then theta is in quadrant 3, so we'll draw a little helper triangle like so. So that this guy, this angle here is theta. Since we're in the third quadrant, the side opposite theta has to be the negative 9. And then 41 would be the hypotenuse. So that we drew our helper triangle just like we did back in chapter 5. Now, the idea here is I want the sine of 2 theta. Oh, well, that simply means I'm going to use the identity, the double identity for sine. Sine 2 theta equals 2 sine theta cosine theta. So write it down, because that identity tells you something. It tells you what you need. It tells you need sine theta. Already got it. But it also tells you need cosine theta. I don't have it. So I need to find it using my helper triangle. Oh, okay, well, let's call the missing side in my helper triangle x. And we know from the good old Pythagorean theorem that x squared plus negative 9 squared is equal to 41 squared. Or x squared is equal to 41 squared minus 81. If I subtract 9 squared from both sides, that's the same as subtracting 81 from both sides. If you actually run this through your calculator, to say 1600. So if you run 41 squared minus 81 through your calculator, you'll get 1600, which means x squared, okay, we have to take the square root of both sides to get x, rather. Take the square root of both sides to get x. Now, this is one situation. Remember when you solve equations like this, how you put a plus or minus right here in front of the radical? In this situation, we actually have to put just a minus. Because x is in the third quadrant, I know it has to be negative. So we actually get x is negative 40. So what does that mean? Well, remember what we're looking for. We're looking for the cosine of theta. So that means that the cosine of theta from our helper triangle, then it's the ka part of SOHCAHTOA. Cosine equals adjacent over hypotenuse. And we just figured out that the adjacent side is negative 40. So we get negative 40 over 41 for the cosine of theta. So we're going to fill this in. We know that the sine of 2 theta is going to be 2 times the sine of negative 41, not negative 9 over 41 rather, times the cosine, excuse me, it's the sine of 2 theta is going to be 2 times negative 9 divided by 41 times negative 40 over 41. So we're going to replace sine theta with negative 9 divided by 41. We're going to replace cosine theta with negative 40 over 41 in the right-hand side of the double angle formula for sine. So we get that the sine of 2 theta is equal to 2 times negative 9 over 41 times negative 40 over 41. And if you just run this through your calculator, you'll get 720 on top, 2 times negative 9 times negative 40, divided by 41 squared, which is 1681. Finally, let's verify this identity. Cosine squared x divided by 2 minus sine squared x divided by 2 equals 1/2 cosecant x times sine 2x. I'm going to start with the left-hand side. So I have cosine squared x over 2 minus sine squared x over 2. Let's see if I can zoom out just one time. And then I work one step to the right. Okay, what does this look like? I'm going to write down a little scratch work, and then I'll have to quickly erase it to get it out of the way. Remember the double angle identity, the first double angle identity I gave you for the cosine of 2 theta. That's equal to the cosine squared theta minus sine squared theta. So what I'm starting with here in green looks like this. Except what's acting like theta is x over 2. So to write this left-hand side as the cosine of 2 theta, I have to replace theta with what it's equal to in terms of this formula, x over 2. And that's exactly what I'm going to do to simplify this, to get it in terms, to get this left-hand side in terms of a single trig function. Because although, you know, kind of looking over here, I'm trying to turn this left-hand side of my identity here into the right-hand side. And although I don't have a single term, I do have a single product. So that seems like a step in the right direction, to write this cosine squared minus sine squared, to write it as a single trig function. It seems like a step in the right direction. That's my intuition talking right there. So I can replace theta with x over 2. That's what's acting like theta here in this identity, in this double angle formula. Okay, so I get cosine. I get that this left-hand side right here is equal to cosine of 2 times theta, which is x over 2. Now I need to erase this scratch work because it's in the way. And you might have already noticed that these guys cancel, and I'm just left with the cosine of x. Oops. So remember, I'm trying to turn this stuff, this cosine x in particular, into this. Looks like I've gone a little bit too far. So let me examine the right-hand side here. So this is scratch work. It can't be part of your identity. You have to, in proving an identity, you have to start with one side and through a series of logical steps end up with the other side. So this is just scratch work. Cosecant x is 1 over sine x. So I'm kind of playing with the right-hand side. And sine of 2x, well, if I use the double angle formula, it's 2 sine x cosine x. Oh. I can turn this cosine x into this, and then I'm golden. How do I do it? All I have to do is multiply by a factor of sine x, divide by a factor of sine x, multiply by a factor of 2, divide by a factor of 2. So I should probably show some of that work. So I'm going to multiply by 2 over 2, multiply by sine x over sine x. I'm really just multiplying by 1. I'm really just multiplying by 1 on the domain where these functions are defined. So it's okay to do. And then I still have the cosine of x. And then I should rearrange the multiplication so that it looks like this. Okay. I'll leave a 1/2 out front. I'll leave a 1 over sine x. I'll put in a times 2. So there's the 2 over 2. All I did was rearrange the multiplication. And then I'll move this sine x right here. Commutative property of multiplication says I can do that. And then I still have that cosine x. And then it becomes clear. You could put this in parentheses and this in parentheses. And it becomes clear what you have by known identities. Oops. You have 1/2. We know that 1 over sine x is cosecant x, so just make that replacement. And we know 2 sine x cosine x is the sine rather of 2x. And if you look, that's exactly the right-hand side we were trying to get. So that's exactly the right-hand side we were trying to get. So we are done.